Hello students, in the previous video Electrostatics part 7 I have discussed about the electric field on the axial position and equatorial position of an electric dipole. If the dipole is ideal or the dipole is normal dipole. Here in this video we are going to discuss about electric field at a general point of the dipole. General point of the dipole means if the point of observation is neither lying on the axial position of the dipole or on the equatorial position. So in this figure you can see this is an ideal dipole. Ideal dipole means length of the dipole is very small as compared to distance r. So to get the value of electric field at a general point, that general point is at point Q, we need to resolve the components of dipole moment P. Here you can see position vector of the point Q is r with respect to center of the dipole. So if we resolve dipole moment P in components, component of the dipole moment along the direction of position vector is P cos theta and component perpendicular to the position vector is P sin theta. In this figure you can see point Q is lying on the axial position of P cos theta component, but point Q is lying on the equatorial position of P sin theta component. So electric field at Q due to P cos theta component, that can be given by the formula for the electric field on the axial position of the dipole. E1 is equal to K 2P cos theta divided by RQ for an ideal dipole. Similarly, electric field due to P sin theta component, E2 is equal to K P sin theta divided by RQ. So what can be the value of net electric field at point Q? That would be vector sum of two electric fields E1 and E2. As the electric fields are vectors, E1 is in the direction of position vector R itself, E2 is perpendicular to direction of position vector R, but parallel to component P sin theta. So E is equal to square root of E1 square plus E2 square by parallelogram law of vector addition, or we can write E is equal to square root of K 2 cos theta divided by RQ whole square plus K into P sin theta divided by RQ whole square. So we can take common KP divided by RQ, and inside the square root remaining square root of 4 cos square theta plus sin square theta. So E is equal to P by RQ square root of 4 cos square theta plus sin square theta. We can divide 4 cos square theta in two parts. 3 cos square theta plus cos square theta plus sin square theta. As we know, cos square theta plus sin square theta is equal to 1. So expression for the electric field remaining at the general point, E is equal to K P divided by RQ square root of 3 cos square theta plus 1. This is the expression. But this formula can be applicable for the previous two cases. If the dipole is ideal and point Q is on the axial position of the dipole, in that condition value of theta is going to be 0 and cosine function cos square theta becomes 1, and the expression is remaining K 2P by RQ, again electric field on the axial position of the dipole. Similarly, if theta is 90 degree, point Q shifts to equatorial position of the dipole. In that condition, expression becomes E is equal to K P divided by RQ. So students, in this part of the video, now we are going to find expression for the torque acting on a dipole if the dipole is placed in an uniform electric field making an angle theta with the direction of the electric field. In this figure you can see electric field is in the direction left to right. This electric field is uniform as represented by the parallel electric lines of force. the dipole moment of the dipole, negative charge of the dipole is here, Q, positive charge here. So dipole moment of the dipole is P. So angle between direction of electric field and dipole is theta. So you can see in the figure, the force acting on the positive charge of the dipole in the presence of this electric field is in the direction left to right, and that force is F1 equals Q into E. At the same time, force acting on the negative charge of the dipole is QE, but direction of this force is opposite to direction of the electric field due to negative charge, and that is given at F2 equals minus Q into E. If question asks what going to be the net force acting on the dipole, so here you can see net force acting on the dipole is F is equal to F1 minus F2. As vectors F1 and F2 are in opposite direction, therefore their sum is 0. So net force acting on the dipole is 0. Now question arises, what is the torque? What is torque? The rotational effect of the couple of two forces. Here you can see in the figure, forces QE in the rightward direction and force QE in the leftward direction. These two forces are forming a couple of force. They are acting on the same entity but in the opposite direction. So this type of forces are called couple of force. So these two forces are trying to rotate the dipole in clockwise direction. They try to align the dipole along the direction of the electric field. Now, how you can find the value of the torque? So we know that torque acting on the dipole is either of the forces of the couple multiplied by moment arm. In the figure, force is Q into E. What is moment arm? Moment arm is perpendicular distance between line of action of the two forces. So moment arm in the figure is BC. So what's going to be the torque acting on the dipole? Tau is equal to force QE multiplied by BC. We can find value of BC as in this figure. If this angle is theta, this angle is theta, corresponding angles. So in triangle ABC, what is the value of sine theta? Perpendicular BC divided by AB. So value of BC is equal to 2L, that is length of the dipole AB multiplied by sine theta. So torque acting on the dipole tau can be written QE multiplied by 2L sine theta, that is moment arm, and we know that Q multiplied by 2L, this is dipole moment P, and electric field E multiplied by sine theta. So as you know, electric field as well as dipole moment, both are vector quantities and they are multiplied as PE sine theta. So torque acting on the dipole is actually cross product of dipole moment of the dipole and electric field E. Now question arises, what can be the value of torque in the different conditions? It means if the dipole is placed along the direction of the electric field, what can be the value of the torque acting on the dipole? So here you can see in the figure, if the dipole is placed along the direction of the electric field itself, then angle between dipole moment and the electric field is 0 degree. So the formula for the torque acting on the dipole tau is equal to PE sin theta. So if theta equals 0 degree, sin theta becomes 0 and torque acting on the dipole is 0. It means if the dipole is already placed along the direction of the electric field itself, there going to be no torque acting on the dipole is try to rotate it in the direction of the electric field. But if the dipole is placed perpendicular to the direction of electric field, in that condition theta is 90 degree and we know that value of the sine function sin theta is 1 and torque acting on the dipole P into E. In this condition the torque going to be maximum, means the electric field try to rotate the dipole with maximum torque. So students, this is a question. A system of two identical dipoles with dipole moment P each is shown in the figure. The system is placed in a uniform electric field E. Find the torque acting on the system of the dipole. So here you can see AB is a dipole, CD is another dipole. The angle between dipole moment of the dipoles is 120 degrees. This is direction of the electric field. So in this question, first of all, you have to find what can be the net dipole moment of the system of two dipoles. With the use of vector sum, you can find net dipole moment. So what is going to be the net